Now that we've seen some of the operations on self-type, in this video we're going to talk about where self-type can be used in COOL. The parser checks that self-type appears only where types are permitted, but that's in fact a little bit too permissive. There are places where some other types can appear, but self-type cannot. And so the purpose of this particular video is to go over the various rules for the usage of self-type. So let's begin with a very simple rule. So self-type is not a class name, and so it can't appear in a class definition. It can neither be the name of the class nor the class that is inherited from. In attribute declarations, the type of an attribute, in this case we have an attribute X and it's declared to have type T, it is okay for T to be self-type. So it's fine to have attributes that are declared to be the self-type of the class. Similarly, it's fine to have local let-bound variables that have type self-type. And it's fine to allocate a new object of type self-type. And what this actually does is that it allocates an object that has the same dynamic type as the self object. So whatever the type of the self object happens to be, which is not necessarily the type of the enclosing class at runtime, the new T operation will create a new object of that dynamic type. The type named in a static dispatch cannot be self-type, again because it has to be an actual class name. Finally, let's consider method definitions. So here's a very simple method definition. It has one formal parameter x of type t, and the method returns something of type t prime. And it turns out that only t prime, only the return type, can be of type self-type. No argument type can be of type self-type. And to see why, I can show it actually two different ways why this has to be the case. And we'll do both because this is actually important. So let's think about a dispatch to this method. So let's say we have some expression e, and we call method m, and we have some argument e prime. And now let's say that the argument e prime has the type t0. So if you recall the rule for method calls, t0 is going to have to be a subtype of the type of the formal parameter. We're going to be passing this in. And so whatever type x is declared to have here has to be a supertype of the type of the actual argument. So that means that t0 is going to have to be a subtype of, and now let's assume that the argument can be of type self-type. So it would be that the t0 has to be a subtype of self-type, and this is in some class C wherever this method is defined. And remember that we said this was always false, that you couldn't have self-type on the right-hand side and a regular type on the left-hand side, because that would lead to problems. That we would never be able to prove that in general for that a type is actually a subtype of self-type, because self-type can vary over all the subtypes of the class C. So that's one way to see that we can't allow method parameters to be type self-type. But it's also helpful to just think about executing the code or some example code and see what can go wrong. So here's an example, and let me just walk you through what happens if we allow a parameter to have type self-type in this particular example. So there are two class definitions. Class A has a method comp for comparison, and it takes one argument of type self-type, and it returns a bool. So the idea here is that the comparison operation probably compares this parameter with the argument and returns true or false. Then there's a second class B, and B is a subtype of A. It inherits from A, and it has one new field, B, little b here of type int. And now the comparison function in class B is overridden. It has the same signature as the comparison function or the comp function in class A, but the method body here accesses the field B. And now let's take a look at what happens with a piece of code that uses these two classes. So here, x is going to be declared to be of type A, but we're going to assign it something of type B. And here notice that there's a gap between the static type, which will be A, and the dynamic type, which will be B, and that's actually key to the problem. And now we invoke the comp method on x, and we pass it a new A object. And so what happens? Well, this type checks just fine because X is in class A, X is of type A, and this argument is also of type A. And so if self-type, if having an argument of type self-type is ever going to work, it has to work for this example where the two static types of the dispatched of the this parameter and the formal parameter are exactly the same. So that clearly has to be allowed if we allow self-type as a type of the argument. And now let's think about what happens when it actually executes. So it's going to invoke the method, the comp method in the B class, okay, because X is of dynamic type B. And then it's going to take the argument and it's going to access its B field. But the argument is of dynamic type A and has no B field. And so this is actually going to cause a runtime crash. So, and just to go over that one more time, just to make sure that it's clear, here X has type A but dynamic type B. The argument has static type A and dynamic type A. And when this method gets invoked, the argument, which is of dynamic type A, does not have the operations, all the fields and methods of the class B, and it results in a runtime, undefined behavior at runtime.